welcome to the course RF transceiver design. We have already discussed in module 1 last week regarding basic of wireless communication. We have gone across all the basic required which will help you to build your basic in communication. Now we are at the core of RF transceiver design. So, we will discuss some of the fundamental related to noise in RF systems. So, welcome to module 2 lecture 7. So, before going to the noise, there are some important units that you should know for any RF system. So, one of the unit you already know and you have studied widely in analog circuit, that is a voltage gain, AV/dB 20 log V out by V in. Similarly, there is a power gain. So, when we are considering power gain, it is a 10 log of P out by P in. So, if you just replace the P out with the voltage quantity, that is a V square by R out, and P in, that is a V square in by R in. So, here if your output power is V square out by R out and output input power is V square in by R in, then if in this case my R in is equal to R out, that means my input impedance is equal to output impedance. For mostly for RF system it is equal to 50 ohm. Then this you can also write your power gain is equal to voltage gain. So, this is a condition you should know if you want to consider power gain is equal to voltage gain. It is valid only when the input and output is matched to the R out. So, there is a one more unit that is important. So, before going to this example, I just want to tell that another unit, that is dBm. This dBm is relative to 1 milliwatt power. So, always remember that dBm is with respect to 1 milliwatt power and it is a absolute quantity. So, for example, if we want to find the power in dBm, we know the power input power, then we just divide by 1 milliwatt and you will get the power in dBm. For example, 0 dBm is nothing but P in is equal to 1 milliwatt. So, I just want to give you the example. Mostly for RF system, we generally means when we are designing anything on chip, what we will try to do is we will consider the voltage swing or voltage gain. So, how you can relate to the power based on the swing. So, in this example what it says, an amplifier senses a sinusoidal and delivers a power of 0 dBm to a load resistance of 50 ohm. So, let us say this is an amplifier and what it does, there is a load resistance RL. So, it delivers 0 dBm to the load resistance. This is a 0 dBm output power. So, what we need to find is determine the peak to peak voltage swing across the load. So, we can directly find out peak to peak voltage swing P out, which is equal to V peak to peak by 2 root 2 square upon RL. So, if we know if 0 dBm, if you try to convert into the power, it is nothing but 1 milliwatt. So, and RL is 50 ohm. So, you can get this is V peak to peak square by 8 RL, which is equal to 1 milliwatt. So, you can get V peak to peak, which is 632 millivolt. So, this is a milliwatt and this is a millivolt. So, this is how when let us say you want to consider the voltage peak to peak, and if you want to convert into the power, this is how you should convert into the power. And always remember that in RF we use a power and in power in dBm. So, dBm is important and that is with respect to 1 milliwatt. So, in the next slide we will see what are the different combination, means how you can use the dBm and other units. So, here this power gain I already told. So, if there is an amplifier is given, there is output power by input power and then voltage gain, that is V out by V in. The only difference is here, if you try to match input and output is matched, then you can directly write power gain is equal to voltage gain. dBm I already discussed. So, always try to remember that when there is input power 30 dBm is applied to an amplifier, and if the amplifier has a gain of 10 dB, then what is the output? So, output is nothing but 30 dBm plus 10, which is equal to 40 dBm. So, always remember dBm plus dB is equal to dBm, because this is a relative, it does not have any unit, however, this has a unit of power. So, now there is another example can also be think that if you have a 2 amplifier and you have added the power. So, let us say if there is a 30 dBm power and then 20 dBm power that you want to add. So, I just want to throw the question, what is dBm plus dBm equal to? So, you might think that dBm plus dBm means 30 plus 20, that is 50, but it is not correct, it is a wrong. So, before going to the 30 dBm or 20 dB, first what you need to do, you need to convert 30 dBm to the equivalent milliwatt power, that is 1000 milliwatt, and 20 dBm you should write a 100 milliwatt. Then you add 100 plus 1000. So, your output here is nothing but 10 log of 1100 milliwatt by 1 milliwatt. That will be come around 30.4 dBm. So, always remember, do not confuse yourself. If you want to add dBm plus dB, the output is dBm, directly you can add, but if you have a 2 power in dBm and if you want to add 30 dB plus 20 dBm, you need to convert into the absolute term and then you add, you will get the final answer. There is one more quantity, that is a dBW. This is mostly used for very high power application, that is dBW. So, it is in the previous example, in previous unit we have considered with respect to milliwatt of power, but if there is a very high power in terms of watt. So, with respect to 1 watt of power, the dBW has been used. And another quantity, that is another units that are widely used is a dBc. So, decibel related to the carrier power. So, let us say I have a certain carrier here, this is a carrier at 1 omega naught, and then there is a desired signal which is lying somewhere here, that is at some omega naught plus delta f. So, this omega naught plus delta f frequency, omega naught plus delta omega, at omega naught plus delta omega frequency, there is some other power, other carrier that we are interested. So, this is a desired carrier and this carrier is just at omega naught. So, if you want to find the power with respect to this carrier, then this carrier has a power of 30 dBm and this has a minus 20 dBm. So, the difference between this will give you 30 dBc. So, the desired signal which is a omega, which is at omega naught plus delta omega, is with respect to the power of omega naught, that is called relative to this omega naught, relative to certain power, certain carrier power at omega naught. So, this is a dBc. dBc has also application when you are dealing with a oscillator or PLL or phase noise. So, it has a various application even when you want to let us define the blockers and blocker power. So, if this is a blocker and this is a desired signal, then you can find out the power with respect to the blocker or the carrier. So, these are the basic units: dBc, dBm, dBw, dB power gain and voltage gain. So, now let us move to the noise of the, that is important, that we are important for this entire course. And as far as any electronic system, there is a noise, and we need to deal with the noise and try to get the signal out. So, we all have studied what is a noise. Noise is nothing but a random process, and it is generated due to the flow of charge carriers in any conductor or semiconductor, because all electronics is in between conductor and semiconductor. So, generation of this due to the random process in the flow of charge carriers in conductor or semiconductor, there is a noise. In certain places it is also generated because of vibrations also. We already know when you send a satellite and when there is a launch vehicle will launch, at that time there is a tremendous vibration is happening in the satellite and whatever system, control system that is made, and that will also add a noise in the system. So, noise can be due to the vibration also, and it can be generated externally or internally, means inside the devices or outside the devices. So, for within the system that we are targeting. Let us say I have a certain amplifier and I have not given any input, but if I have a accurate spectrum, then still if you have a supply the DC, you will get some output, and that output power, that is called a noise floor of the system. You will get some noise floor across the bandwidth. This is typically less than minus 100 dBm for the bandwidth of the system, and it can go up to value of minus 174, that we will see more in detail in this class. And noise is generated by a random motion of charge carriers in devices or materials. So, these are the basic various definitions of noise in various literature you can come across. Now, what are the sources of noise, that we will see in the next slide. So, one of the noise source that is available in the electron tube or any solid state devices is a short noise, and this is because of random fluctuation of charges in any solid state device or electron tubes. The another noise that is widely used and we study also widely, and it has a more impact on any electronic system, that is the thermal noise. So, that is why it is also called a basic noise. You should have a basic idea of thermal noise, and it is mostly caused by the thermal vibration of charges. Sometimes it is also called as a Johnson or Nyquist noise in some of the literature. So, it has various names: Johnson's noise, Nyquist noise, or basically it is known as a thermal noise. We will see about thermal noise more in detail. Another noise that we will see, it is a flicker noise. So, this is due to the trap charges. So, the charge is, let us say for example, I will just give the example of MOSFET. So, there is a, this is a MOSFET N plus and there is a gate. Now, in silicon oxide there is an insulator SiO2. So, in there is a silicon oxide, if there is some traps are there and that traps will add, means due to this trap charges there is a noise, and this noise is mostly dominant at very low frequency. So, this noise, flicker noise is inversely proportional to 1 by f. So, at low frequency it is very much important to consider the flicker noise. So, trap charges might be there in any solid state devices which has a different combination of materials that we will use, and the electrons will be trapped. So, another noise is a plasma noise. So, due to plasmons, it is caused by the random motion of charges in ionized gas or in sparking electrical components. So, this is mostly related to the plasmons, and where there is a behavior like a plasma, then this noise is occur. So, as far as electronic system is concerned, we means this noise is not studied that much. Then another is a quantum noise. It is very significant and results from a quantized the number of photons and charge carrier. So, because when we are considering the at the quantum means at quantum effect, at that time this quantum noise also we should consider. Let us say for example, if you are making any quantum devices, for that you should consider quantum noise as well. Another noise which is widely known as a popcorn noise, that is a burst noise. It is a low frequency noise and it is found in any integrated circuit or discrete transistor, and mostly it is due to the heavy metal ion contamination, and when there is a gold doped devices it will show the very high burst noise. So, how exactly the burst noise will be, the at the amplitude you will have a burst. So, that is why it is called the burst, and if you try to play in the loudspeaker, because it is in the frequency range of the audio signal, then it will have a something like sound like a popping sound, and that is why it is also known as a popcorn noise as well. So, at low frequency this also is dominated, and when you try to plot this in the oscilloscope you will get the waveform like this. And the final is avalanche noise. So, when the in any device where there is a avalanche breakdown will occur, let us say mostly in PN junction, that time or in Zener diode we will see mostly the avalanche noise, and the cumulative electron hole recombination process by colliding the silicon atoms creates a large noise spikes, and the noise is always associated with the direct current flow. So, this is related when we are using a diode in reverse bias, and mostly for Zener diode it is considered. So, this is also one kind of noise, that is, this is a noise source. There are, so all these are the noise source, and when we are designing a circuit or system we should consider in while making the complete system. We will just give I will just brief the short noise and its equation. We will study the thermal noise more in detail. So, in here in short noise it is associated with the direct current flow. It is present in diodes, even MOS transistor and bipolar transistor. So, here the diode example is given. So, if there is a PN junction, so there is a PN junction, and in there is a depletion region. So, this is a depletion region. Now, what will happen? You need a certain amount of voltage so that electron from n type will move to the p type and hole will move from p type to n type, and that after applying that built in potential your electron and hole will move. Now, this when the current is flowing, there is a possibility that this current will not be the constant, means when we see the current, it looks like a constant, but there is some variation because the amount of electron and hole that are moving, that numbers might change, and that will create little bit of the noise, and this noise is called as a short noise. So, the current I is composed of a series of random independent pulses with average value ID, and then the mean square value of noise current. So, noise current generally is given by 2q, here it is ID into delta f. So, this is a mean square value of a noise current. So, if this is a junction diode and if we try to make a small signal equivalent circuit, then this is a resistance RD KT by QD given by KT by QD, and this is a noise, that is a 2QID in delta F. So, this is a noise current for this short noise. Now, we will see the when we discuss the BJT, or mostly it is dominant in BJT. So, we will see this noise in detail for BJT circuits, and for all other components thermal noise is important. So, thermal noise, it is a random in nature. So, I just want to give the example here. If you have any resistor and that resistor at temperature T Kelvin, if you try to observe the voltage at Vt, means across the resistor, if you try to observe the voltage, and if you have a good oscilloscope, then you will get the voltage waveform which is a random in nature, and that is a random across. So, here the due to this random process, you have a noise, and that noise is a thermal noise, because of the thermal effect this is happening. So, the average value of this noise voltage is 0. However, the RMS value is given by the Planck's black body radiation law, and it is the equation, what is the noise. So, if I want to find the noise voltage Vn, that will be given by square root of 4 HFBr e raised to HF by kT minus 1. So, here H is nothing but Planck constant, K is the Boltzmann constant, T is the temperature degree in Kelvin, always remember this is in Kelvin, bandwidth is in hertz, center frequency and the resistance R. Now, in this equation, if your HF is much less than the KT, if HF is much if HF is much less than the KT, then HF by KT minus 1 is approximately HF by KT. So, you can replace in this equation, this equation has a 4 HF Br, this is HF by KT e raised to HF by KT minus 1, you can write 4 HF Br HF by KT, this will be cancelled out and you will get, so this is all square root, you will get square root 4 kT BR. So, this is a noise voltage, noise, and it is also has a Vn, which is a square root of 4 kT BR, and this noise is independent of the frequency, because here this HF we have, and it is depend upon the bandwidth of the system. So, here now if I want to add, the unit of this is a volt by square root hertz. It is also, if I will take the bandwidth at other side, this Vn by square root B, which is equal to 4 kT R. So, this is also considered the unit of this noise voltage is also volt by square root hertz. We will see other units also in the next slide. So, generally this noise source are defined in terms of power spectral density, and how the power spectral density is find out. Let us say if I have a certain signal xt, and if I will pass that xt input to the filter, which is a bandwidth of 1 hertz and centered at frequency f1. So, how the PST has been find out, if this is a xt which is input and that is given to the filter, which is a bandwidth of 1 hertz and centered at f1 frequency. Again I will square the value, whatever output I will get, I will square, and that will give us the xf1t square will give us the power spectral density. So, that value I will plot it here, that is at f1 frequency. Similarly, you can give to the f2, then f3, so a different filter, and then you can plot the power spectral density for entire frequency range from f1 to fn, and this is denoted by Sxf. So, power spectral density various, you can also define the power present in the signal as a function of frequency. It is also tell us how much power the signal carries at each frequency. So, if you know the PST, you can also find out that at each frequency how much power it carries, and PST which is Sxf of the waveform xt is defined as the average power carried by a filter. So, whatever I explained, that same thing is written in words here, that xt is defined as the average power carried by a filter with a center frequency of f1 and bandwidth of 1 hertz. So, it has a different units that is considered. One of the unit is, if you see in the last slide, if I will take the square of this term, I will get a Vn square, which is a 4 kT BR, and if I will take the bandwidth bottom, then 4 kT R. So, this is nothing but the volt square per hertz. It is also mentioned in terms of volt square per hertz. It is also, so if you try to plot the white noise, so now, so white noise is independent of frequency or bandwidth. So, if I will divide it with the bandwidth, and I will get the, for any resistance, the white noise is 4 kT R, and the unit is volt square per hertz. Sometimes it is also mentioned in, if you mention in dBm, it is also mentioned in dBm per hertz. So, it has a 3 units, one is a volt square per hertz, another is dBm per hertz, or it can also written as a volt by square root hertz. So, these 3 units are there, are used for noise, to represent the noise voltage. And here this is a frequency and this is a power spectral density Sxf. So, now if we try to consider there is a one band pass filter. So, there is one resistor, and if I want to make that resistor a noiseless resistor, I will add the noise. So, this is resistor which is a noise voltage V n, and then how much power it will deliver to the other resistor R. So, I can write here, we can write here P n, which is I square I, the noise power. Now, current I here is given by V n square by 2 R, because there is a total resistance is a 2 R multiplied with the R. Then you will get V n square by 4 R. So, now if I will replace the V n square by 4 R is equal to 4 K T B R, then I will get the final answer K T B. So, this is a K T B is a maximum available noise power from a noisy resistor at temperature T Kelvin. What is KTB? KTB is the maximum available noise power. So, let us say I have a noisy resistor and its noise power, if I were to find out, that is the maximum noise power, and this will give us the important understanding. Let us say if your bandwidth of system is 0, then your output power is 0. If your temperature is 0, then your output power is 0. If your bandwidth is infinity, then your output power is infinity. So, here the noise power is also denoted as the N naught and its equivalent temperature T E. So, you can also write N naught in terms of K T E B, and your equivalent temperature can also be find out with T E N naught by K B. So, this is a basic of thermal noise, and in this class we have seen all the noise sources which are there and we should consider while making any electronic system or RF design. We will discuss more in detail about thermal noise and other effects of thermal noise more in detail in the next class. Thank you.